Well, I asked to implement this method. Here we see the correct solution. This is a function that that is a left-hand side of the equation. For example, x minus cosine x equals to 0. Suppose that they are going to find the root of this equation, x minus cosine x equals to 0. We should write this function that takes x as a parameter and returns the value of the function x minus cosine x. And after that, the function that implements the bisection method. Here in this implementation, the method is implemented in main function, not as a separate function, but just in main. What we should write here? We should declare the left and right points a and b. Suppose that a and b are 0 and 2. Then the variable for the middle point, c. Next parameter, tolerance. Suppose that tolerance is 10 power minus 12. Do you remember this notation? 1e minus 12. What does it mean? It's a notation for power. 10, the symbol e means 10 in some raised in some power. Here 10 power minus 12. If I write 1e minus 12, it means 10 power minus 12. For example, 1.1 e minus 12 means 1.1 times 10 power minus 12. So the tolerance is very small, 10 power minus 12. The number of iterations, 200. It's a maximum number of iterations. And k is a counter, the counter for the iterations performed. According to the method, what is the stop condition? Here the stop condition is written two times. The first stop condition is I smaller than n, and the second stop condition is that the length of the interval is smaller than tolerance, or the value of the function is smaller than tolerance. I write these conditions here. Or if you want, I can write it exactly as written in pseudocode. If b minus a over 2, if b minus a over 2 smaller than tolerance, right? Smaller than tolerance. And okay, it's enough to write just one condition. Then break. It's one condition. The second condition is f of c smaller than tolerance. Oh, yes, if you want, I can write it here, or module f of smaller than tolerance. Well, in this case, the method should stop. Otherwise, we compute the middle point C. After that, we check the sign and change these points and increase the count. So the second condition here I can omit. I can use only a condition on the length of the interval. And when the method stops, if the counter of the iterations equals to the maximum number of iterations, it means that the method failed to solve the problem. And if the k smaller than n, in this case, it means that we solved the problem and we obtain the solution. Let's check. And you see that we find the solution after 40 iterations. Let me increase the font. The solution is 7.38, and we get it after 40 iterations. So we should repeat this process 40 times. But again, this condition I can write it here. I can write it here.
So you repeat the iteration how many times?
I run it again now, and you see that the method converts after 40 iterations. Well, yeah, the method stops when the interval becomes small. When the interval becomes smaller than tolerance. If the interval is large, then the method continues. What happens if we take very large tolerance? For example, 10 power minus 1, 0.1. It's just a few iterations and the method stops. Let's check it. Just 4 iterations, but see that the solution is rather wrong. 0.625. Let's check the quality of the solution. How to check the quality of the solution? Because at the real point of the solution, f of this point, f of x, must equals to 0. Let's output here the value f of e. I just output f of c equals to and f of c. Let's output to the screen the value at the point that we find. And you see that the value of f of 0.625 is minus 0.185. It's not close to 0 because we take a large value of tolerance. Let's take tolerance smaller. 1e minus 2. It means 0.01. I can write it in the usual notation, 0.01. And you see that the number of iterations increased, and the value is 734, and the value of the function becomes closer to 0 at this point. If I decrease the tolerance, let's take 0.001. The number of iterations increased, and the value becomes closer to 0. I think you understand, the smaller we take the tolerance, the more correct solution we get. Let's take the tolerance 10 power minus 6, 0.00001. 20 iterations, but this solution is precise. What is this value? F of. Do you understand what is written here? Minus 1.4 times 10. E means times 10, and then times 10. What power?
To power
Negative 6.
negative 6.
10 power negative 6. It's a very small value. 10 power negative 6. It's a very small value. So this solution is very close to the real solution. If I decrease tolerance more, for example, 10 power minus 8, the method requires 27 iterations, and we get the solution that is very, very close to the real solution. The value of f of c is minus 1, yes, negative 8. But it requires 27 iterations. So the smaller tolerance we get, the more number of iterations we should carry it out to find the solution. Well, suppose we have a resource only for 20 iterations. We have time to implement only 20 iterations. But I want to solve this problem with tolerance 10 power minus 8. The method failed to solve this problem. Do you remember that it requires 27 iterations? So 20 iterations is not enough. 20 iterations is not enough to solve this problem. But if I increase the number of iterations, for example, 50 it's okay. 50 it's okay, but if I take, for example, tolerance 10 power minus 14, if I want to solve this problem precisely, or 50 it's still be enough, but 40 is not enough because it's required 47 iterations. Well, again, I say that this solution you can find in the video file. I will send you the video of this lesson. And also you can find any other solution. Just type bisection method C++ and you can find. Of course, this solution is slightly different from my solution, but the idea is the same.
So, will it be okay for doing any type of solution?
Sorry?
Well, is it going to be okay if I bring my own type of solution?
Okay. Well, any questions about the method? Okay, if you don't have questions, let's discuss about error of the method. Well, I show you in these examples that when I run this solution in Visual Studio, you see that we never find the real solution. We never find it. We find an approximation to the real solution, and this approximation depends on tolerance. If I take tolerance 0.1, I get the point that lies rather far from the real solution. But if I take the tolerance, for example, 10 power minus 10, in this case, the method outputs the solution that will be very close to the real solution. And you see that the number of iterations depends on tolerance. And the question is how many iterations we need to carry out to find the solution with the given tolerance. And this theorem helps us to answer this question. To analyze the bisection method, let's consider the sequence of intervals that arise in the process of solving. And let's denote the first interval as A0, B0, A0, B0. This is the first interval, the initial interval. The next interval, the half of this interval, A1, B1. And so on, A2, B2, and so on. What can we say about these intervals? I can say that the next interval is the half of the previous interval, right? This is the first A0, B0, A1, B1 will be left or right half. I don't know what half, but it's a half. For example, A1, B1. A2, B2 will be the half of this half, 1/4. For example, A2, B2, and so on. So the next interval is twice smaller than previous one. And according to these properties, I can say that A0 is smaller than A1, smaller than A2, and so on. And any of value of A will be smaller than B0. And any value of B is greater than A0. And the main property, the main point is property number 3. Let me show it in full screen. The main property is property number 3. I already told you this property that the length of the interval number n plus 1, it's half of the length of the current interval. So that b n plus 1 minus a n plus 1 equals to 0.5 b n minus a n. And if we apply the property number 3 repeatedly, we find that the length of the interval number n, bn minus an, equals to 2 power minus n times length of the first interval, b0 minus a0. It's very simple to find. This is the length of the first interval, b0 minus a0. What is the length of the first, the interval number 1? b1 minus a1 equals to 1 over 2, 1/2, or 0.5 b0 minus a0. 2 times smaller. And after that, I apply the same for the next interval, that b2 minus a2 equals to 0.5 b1 minus a1. And at the same time, it will be 0.5 power 2. But what is 0.5 power 2? Is 1 over 2 power 2, and 1 over 2 power 2 is 2 power minus 2. So if I repeat this process n times, I get 2 power minus n times b0 minus a0. This is the main point. And if we suppose that we carried out infinitely many steps, then I can say that the limit is 0. And if the limit of this value is 0, I can say that bn and an tends to the root of the equation f of x equals to 0. Suppose that at a certain step of the process, the interval number n, an, bn, has just been defined. If the process is stopped now, of course we can take as approximation to the solution left or right point of the interval, but an or bn are not very good approximation to the real solution. The better approximation is the middle point, Cn. Cn that computes as an plus bn over 2. Let me write it here. the formula is on presentation, but I write the picture on the board. Suppose that this is the point AN. Suppose that this is the point BN. And somewhere between AN and BN, there is a point of the real solution. The point where function intersects the real line. This is a point of the root of the function, and here it's denoted as R. Small or large? Let me write large. This is a root point. I can take A as approximation to the root. I can take B as approximation to the root. But actually, it's better to take Cn as approximation to the root. And what will be the mistake? What will be the error? Error is a difference between unknown root and Cn. R minus Cn. This is the error, absolute error. And the absolute error is smaller or equals that 1 over 2 bn minus n, that smaller or equals 2 power minus n plus 1 b0 minus a0. And this formula tells us that the error that we get after n steps will be smaller than 2 power minus n plus 1 times b0 minus a0. And all of this is formulated in the form of this theorem. If a0, b0, a1, b1, and so on, an, bn, denote the intervals in the bisection method, then the limits of an, of the sequence an, and limit of sequence bn exist, are equal, and represent the zero of a function. If R is a real root and Cn is a middle point of the interval number n, then R minus Cn smaller or equals 2 power minus n plus 1 times b0 minus a0. Any questions about this?
I don't understand the last one. Minus Cn, why is the mistake?
Again, this is the root. We don't know it. We are going to find it, but we don't know it. We have the interval from A to B, and we have the middle point C. We take C will be approximation of this value. How to find the error? It's a difference between C and A. It's a difference between these two values, R minus Cn. And this upper bound tells us that after n steps of the method, we will get this error smaller than this value. Well, and let's consider some examples. Suppose that the bisection method is started with the interval from 50 to 63, and how many steps should be taken to compute a root with relative error equals to 10 power minus 12. Well, please read this example. Read the task again. Well, wait a minute.
The only guy that can, I know he can do more for that was an French person. There's only one guy in 7. He can bench like 200. I swear. But for me to pull up, I don't think he can do it. I swear. If he can bench 200, 210. This is how we work. Even me. The one we can one
Well, again, the initial interval is from 50 to 63. And the question is, how many steps of the method should be carried out to get the relative accuracy, relative error, 10 power minus 12. Well, I stress that here I don't specify the function. It doesn't matter what function, what root we are going to find. The main point here is that the length of the initial interval is given. How to solve this problem? The solution is written here. Again, let's denote R as a real root, and Cn is an approximation that we get on the step number n. R minus Cn is the absolute error. R minus Cn is absolute error. On the first lesson, we'll consider not only the absolute error, but also relative error. Relative error is R minus Cn over R. And according to the problem statement, the relative error, it's all written here. I just repeat this on the board. What?
This slide.
Yes, of course, I send you the video, I send you the slides. Of course, sure. These values, these ratio should be smaller or equals 10 power minus 12. according to the problem, r is greater than 50. Because the interval is from 50 to 63. That's why the real root, it must be greater than 50. And in this inequality, I can replace here, I can write here over 50. And after that, I can apply the theorem. I can apply this theorem. According to this theorem, r minus cn smaller or equals 2 power minus n plus 1 times b0 minus a0. What is b0 minus 50? Yes, it's a 13. It's a 13. 63 minus 50, it's 13. And after that, I can substitute this inequality here, and I get this inequality that 2 power minus n plus 1 times 30 over 50 smaller than n power minus 12. And after that, we should solve it for n. We should find that the n there that satisfies this inequality. How to find it? This step is omitted here, but I think it's over. First, we should move to the right. We should move 13 over 50 to the right. 2 power minus n plus 1 smaller than 50 over 13 times 10 power minus 12. And after that, the main point, how to solve such inequalities. Do you remember or not? If the unknown variable is in a power.
2 over 2. So you got minus n plus 1 smaller than 2 over 15.
So, here is 2 in some negative power, right? And in the right hand side is a constant, right? It's just a number, it's just a constant. So I can write this inequality as 2 power minus x smaller than some constant. Right? This is the form of this inequality. And we need to find the x. Maybe x is not good. Let me use n. 2 power minus n smaller than constant. How to solve this inequality? How to find the n?
Minus n smaller than 2 over 1.
You should apply logarithm to both parts. If the unknown value,
2 over 2, yeah, I thought that that's the
because if you apply logarithm, that n,
yeah,
if you apply logarithm 2, if you write here just
minus
log
n
2
logarithm constant.
and log 2 constant, log 2 of this constant, logarithm 2 power minus n,
n.
you can move minus n before the logarithm, and after that you simply find the n. Please compute, please find the n using this idea, and the correct answer is that n will be greater than 37. So it's enough 37 steps to find the solution with the given tolerance. N is greater than 37. And let's check it. Of course, I take some another interval. Here we have the length of the interval of the initial interval 13. In this example, the length of the interval is 2, b minus a. But let me take the same tolerance, 10 power minus 12, as in this example. And you see that 40 iterations. This inequality gives us that should be greater than 37, and here we get 40. So more or less the same answer. We have more or less the same answer. So the meaning of this theorem is that it can tell us in advance how many steps of the method we should carry out to find the solution with the given tolerance before we run the method. Well, to understand it, I ask you to try to solve the exercises number 3 and 4 exactly on the same way as this example is solved. Only we take another intervals and another tolerance, another value of tolerance. Well, do you have any questions about the method? No questions. Okay. And other students who connect using Teams? No questions. Good, very good. Well, if you don't have questions about the bisection method, let's discuss about the next method. The second method that we consider is called Newton's method. Newton's method is very general method that can be applied in many situations. And here we consider the application of the Newton method to the problem of finding the zero value of a function. And the theoretical basis of Newton method is Taylor formula. I wrote you this formula on the first lesson, Taylor formula, and I told you that we will use it very often. And we will use the notion of limit very often and Taylor formula. Let me remind you that Taylor formula, the Taylor formula allows us to compute the value of the function at some point using the values of the function at other points, at other point x. And we apply here this idea to find the root. Again, suppose that this is the interval and this is the point x. X we take as approximation to the root. And this is the root. R, unknown root. I use the same notation for root. And this is the point x. And let's consider the difference between root and x as some step h. So this interval, the length of this interval, let's denote it as h. In this case, I can say that r equals to x plus h. R equals to x plus h. Again, let me repeat that R is unknown root. After that, I can say that as far as R is a root, f of R equals to 0. So the left equation, the left equality here, 0 equals to f of R, because R is a root. And next, it equals to f of x plus h, because I suppose I write that R equals to x plus h. And after that, I can say, according to the Taylor's theorem, that it equals to f of x plus, I just write on the board the same formula, h times the first derivative at the point x plus terms OH squared. This notation OH squared denotes the terms that includes h power 2 and greater. This term, the first one, includes h power 0. Any number in power 0 is 1, right? This term includes h power 1. And all of these terms, it will, here it's infinity many terms. It includes h power 2, h power 3, h power 4, and so on. And all of these terms can be denoted as OH squared. The terms that includes h squared and greater.
Same. Just a small question. F is interval between x and 2 or x and r.
What?
H
H is the distance of this, the length.
between x and 2 or x and r.
X and R, it's R. Let me write it in as capital. It's R. It's not 2, it's R. It's a root. Ah. Well, and the next our supposition is that x is close to R. It's not very far. And in this case, h will be small. And what happens if h is small? For example, what I mean small? What I mean by the word small? Not I, but in mathematics. When somebody tells that some value is small, it means significantly smaller than 1. So we suppose that h is not smaller, but significantly smaller than 1. This sign, 2 times smaller, means that significantly smaller than 1. For example, h may be 0.01 or smaller. Maybe 0.1, but not greater than 0.1. Well, if suppose that h is, for example, equals to 0.01, what can you say about these terms? What can you say about h squared? If h is 0.01, what is the value of h squared? What?
0.1.
0.1? No. What is h? H equals to 0.01 h squared. Take your pen, take your paper, and compute it if you cannot compute it in mind. Because 0.1 is the wrong answer. Or calculator, run calculator on your computer. 0.2? No. Use calculator. Our subject is called computing mathematics. Of course, 0.301. Right. I can say for simplicity that I can write it using powers. H equals to 10 power minus 2, sorry. right, 10 power minus 2, and h squared in this case. What would be the value of h squared?
Minus 3. Return minus 4.
Minus 4. You should multiply powers. H squared is
Yeah.
10 power minus 4. What can you say about h cubed?
Let's go minus 6. Minus 6.
Minus 6. You should multiply.
Yeah.
Multiply powers. H cubed equals 10 power minus 6. So my point is that if h is small, h squared will be
Smaller.
smaller, h cubed will be smaller, and these terms that have the powers h squared and greater can be ignored. Of course with some error, of course with some small error, but if h is small, h squared will be smaller, and we can ignore it. We can ignore these terms. We can ignore these terms if we suppose that h is rather small. And what we have, let me write from the left to right, right? 0 equals to f of x plus h times f of x, f prime x. 0 equals to f of x plus h times f prime x. And from this we can derive that h equals to, I just, again, it's all written on the slides, that h equals to minus f of x over f prime x. And this formula gives us that if x is an approximation to root, then x plus h will be better approximation of the root. If these terms will be 0, in this case we have exact value of root. But as far as we are not sure that these terms are 0, we are sure that these terms are very, very small. In this case, x plus h gives us not exact value of the root, but some value that is very close to the root. Do you understand the idea or not? Not yet. Well, let's have a break now. According to the schedule, we should have a break, and after the break, we continue. Let me close there. Well, I close the screen now, and after the break we continue. Any questions from the students who are online or not?
Maybe I will come there if I see the environment. I don't want to always talk, but it's in my headset.
No questions.
That's what I'm doing.
Okay, we continue our lesson after the break. 10 minutes, 10 or 15 minutes break. Let me share the screen for the students who are online, and let's continue. Well, again, let me repeat here the main points. R is a root, but we don't know it. X is some approximation to this root. And using this X, we want to improve this approximation. We want to find the better approximation to the root that we have. And suppose that we know the exact value of h. And in this case, I can say that x plus h will be the real root. And it will be true if we take all the terms in the Taylor's formula. But if we truncate the terms of h power 2 and greater, this h will be not the real length, the real distance between r and x. And if we take x plus h, where h is minus f of x over f prime x, it will be not exact root, but just the better approximation to root. And we can repeat this process step by step. The main formula is written here on this slide. Suppose that we have some first point, initial point, x0. x0 is the initial point. R is a known root. Again, I repeat this. If suppose that somebody tells me the right value of h, and after that I can say just x0 plus h will be the real root. But nobody tells me the real value of h. This formula gives me some approximation, and I compute the point x1 that will be closer to the real root. And after that, using x1, I compute x2 that will be closer to the real root. And again and again. And this formula tells us how to compute these values. How to compute x n plus 1 using xn. xn plus 1 equals to xn minus f of xn over f of f prime xn. Using x0, I compute x1. Using x1, I compute x2. Using x2, I compute x3. Where I should stop, where the process should be stopped. Like in bisection method, I can apply two criteria. The value of the function is smaller than tolerance, or the length of the interval is smaller than tolerance. I can take this tolerance as some small numbers, different or the same number. The value of the function, the absolute value is smaller than tolerance, or the length of the interval, x n plus 1 minus xn smaller than some tolerance. To understand how this method works, we solve some simple problem. And also I want to show you some graphical, I want to discuss about some graphical interpretation before we apply, before we try to solve this, try to apply this problem. And from the description, we can say that Newton methods involves linearizing the function. It means that f of x was replaced by a linear function. And using this linear function, we find the next point that is closer to the root. The real value of the function f of x can be written using Taylor's series as f of c plus f prime c times c minus x minus c plus 1 over 2 factorial, second derivative, f of c, and so on. But again, linearization means that we truncate, we remove all the terms that have power 2 or greater. We consider only the terms of power 1, linear term. And instead of f of x, that is some nonlinear function, some complex function, we consider L of x, that is linear. C is a constant. F of c is a constant. F prime c is a constant. X is a variable. And L of x is linear. Because we delete all of the terms that includes x power 2, x power 3, x power 4, and so on. Do you remember the graphical interpretation of a derivative? What is the derivative of a function? I asked you this question on the first lesson. Do you remember what is the derivative of a function? And the graphical interpretation of the derivative. It's not a definition, unfortunately. Suppose that this is a graph of the function, like this. Suppose that function looks like this. And suppose that we consider this point. What is the graphical interpretation of derivative? Graphical interpretation of a function I already draw on the board. This is a graph of the function f of x. But what is the meaning of the derivative at some point c? Do you remember it or not? I think you should consider such things on mathematical analysis, that the value of the derivative is the slope of the tangent line at this point. So I can take the sum point, let the notice as x, this point xn, and suppose that I know the derivative at this point. F prime at the point xn. F prime at the point xn. F prime at the point xn. The value of the derivative is the slope of the tangent line. I can draw a tangent line that passes through this point. And I can say that this tangent line is a more or less a good approximation to the function. Of course, this line is very good approximation near this point, and it's rather bad approximation far from this point, right? But I can say that tangent line is a more or less good approximation. And the point of intersection of the tangent line and the line x can be considered as a more correct approximation of unknown root. This is root, this is root, this is current point xn, this is the point xn plus 1. And we can take the point xn plus 1 as a point of intersection of the tangent line and the zero line. What is the next step? How to compute the next point, xn plus 2? We should repeat this process again. I compute f of xn plus 1. I compute the derivative f of f prime xn plus 1. I draw a tangent line. And I take the point xn plus 2 as a point of intersection of this new tangent line and the zero line. After that, I can compute xn plus 3, n plus 4, and so on. Well, I think this picture illustrates that the next point will be closer to the root than the previous one. Closer, 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 and closer. This is a graphical interpretation of the Newton method. Well, to understand how this method works, let's apply it to a very simple problem. Very simple problem. Do you know what is the square root of 4? Square root of 4. 2. Square root of 3. Well, we know that square root of 4 is 2, but we don't know the square root of 3.
1 comma something, somewhere.
Yes, yes, but how to find it? How to find square root of 3? How to find square root of 5? How to find square root of 6? We can find it using this method. And actually, exactly this method is implemented in the function sqrt in when you call in C++ or in Python or in some other programming language the function of computing square roots. This function calls this method. Well, so the goal is how to find square root. How to find square root. Yes, this example is written here on this slide, but I don't want to show you. Well, maybe I where is this picture? Well, I freeze here on this picture and I show for the students who are online this slide, because the information from this slide we will write on a board. This is a formula. This is a formula. The formula is written here. The formula is written here. And the goal is to find square root of some number, right? Let's denote this number as R. And the goal is to find square root of R. We can solve this problem for number 4. Square root of 4 is 2. Square root of 9. Square root of 9.
3 point something.
Why something? Square root of 9.
It's 3.
3.0. Why something? Of course, I can say that 3 point something. And this something is exactly 0. But square root of 10 is 3 point something. Square root of 9 is 3.0. So the goal is to find square root of some number. Or I can write it like this, right? Square root of some number. We don't know this square root. Let's denote this value as x. X equals to square root of so, x equals to square root of 5, square root of 3, square root of 10. Well, I can raise this equality in power 2. What happens? X square equals to r. Right? I just raised it in square. And the final step, let's formulate this problem in terms of the root finding problem. F of x equals to x squared minus r equals to 0. I just move r to the left side, and as far as x is square root of r, x squared minus r must be 0. And I can say that this is a function, and the root of this function will be square root of r. Okay. Let's apply Newton method to find the root of this function. How to apply? We should somehow reformulate this formula for this problem. We should reformulate this problem, this formula. This formula is written for arbitrary function, any function. In our case, we have particular specific function x squared minus r. What you should do is just to substitute our function into this formula and derive particular formula. I forget all the mathematics. Please help me to do it. I forget all these things. Please help me.
You just will help you that you just go direct. You just substitute. You just substitute to show you.
Or the
Well, if you are going to do some other, if you don't listen to me,
I listen.
but come here and solve this problem if you listen.
To show you.
Well, can you substitute? Come on. So,
Man. I said it helping you.
what is f of x? F of x is written. What we should do to solve this? What we should do first to apply this formula? What we should do?
find the roots.
Look to this formula. Look to this formula. It includes
You just put the f leaves and find the derivative.
yes. First, we need to find the derivative. First, we need to find the derivative. Please write f prime x,
Equal to f.
f prime x. How to find the derivative? Do
F prime and then x.
f prime x, right?
Question X.
X? No.
No.
2x.
2x. Right? This is a derivative. It's a very simple function, and the derivative is very simple, just 2x. After that,
X and plus 1 equal
after that, you should substitute. write f prime x to x. Good. And after that, I ask you just to substitute these, our particular case in this formula. Xn plus 1, x,
Xn minus.
write it here, write it here, write it here.
Okay.
Xn plus 1 equals to
Xn minus
X
x.
Fx.
Xn.
do you understand?
Okay.
Do you understand?
Okay.
or
Yes.
not?
Yes.
Xn
Minus
what?
x squared.
X squared minus R.
Just from
Do
place.
you understand?
Yes. X squared minus.
No.
Do you understand this
Squared minus
notation?
r.
What is the meaning of f of
X
xn?
squared minus r.
F of X is 1 with X squared minus
It's right in
minus
there.
R.
X
Oh.
xn square
Because X squared minus R.
but xn, x number n, not arbitrary x.
Okay.
Xn squared, right? Xn squared.
Yeah.
Okay,
Over
over.
2x.
Over the whole. Or the,
No, not the whole.
Look to
last
this
one.
formula.
okay.
Is it all over or
No.
just?
I see. Over
2x, but not 2x, but 2xn. 2xn because we take particular n. Right. So this answer is correct, and after that we can simplify it. We can simplify this answer. For example, you can write these fractions separately. X squared over 2x plus r over 2x. Please simplify this formula.
yeah. You can come. You can rest him.
This simplification is very simple. Well, what I ask you to do? Xn minus. The first term will be the same. Xn
X squared is fraction
minus and
X Xn squared. Sn squared over
Over
2xn
2x.
minus I over
plus, because minus on minus gives plus.
Plus
2xn.
So
xn.
this is the first term, you're right. Xn squared over 2xn. And the second term r over 2xn. Okay. Equals, what can you say here? Minus xn squared, right? Square. Xn squared over 2xn. 1 x can be cancelled.
Yeah. Cancel x. And x. 1x is there.
So the one negative
Xn, right. Xn over 2 plus r over 2xn. Well, look to first two terms. We have xn minus xn over 2. What can xn minus xn over 2?
Should be xn over 2.
Yes, just clean the first xn. So
Yeah.
xn with minus. Delete it. Okay. Well, and finally, what we have here? Xn over 2 plus r over 2xn. Let's move 1 over 2 outside of the brackets. And you can write 1 over 2 bracket xn plus r over xn. And the close bracket. Well, that's all, and we get the formula that is written here.
Oh.
X plus xn plus 1 equals to 1 over 2 xn plus r over xn. Let's apply this formula. So this formula is written here on this slide. This formula we derive it on the board. And now let's try to compute square root of 3. How to compute square root 3? How to start this process? How to start this process? We need to know the first point. We need to know the first point, x.
X equals.
We need to know the first point. What can we take as the first point for square root 3? For example, again, suppose that r equals to 3. And we are going to find square root of 3. Yes, this is the formula. This is the formula. This formula, let me write it here. Xn plus 1 equals to 1 over 2 xn plus, if r is 3, is 3 over xn, right? Or just r for in general case. When in our case r equals to 3. How to apply it? We need to know the first point, x0. We need to know x0. And if we are going to find root of 3, what can we take as an approximation to this root? We are going to find square root of 3. Do you know this value, square root of 3? No. But can we have can you guess where it is? Can it be 10? No. Can it be 5? What value? Square root of 4. Square root of 4. What is the square root of 4? 2. Square root of 3 should be smaller than 2, right? It cannot be greater than 2. We know square root of 4, and we can, square root of 4 is 2, and we can take 2 as initial guess for square root of 3. Its initial guess. Our supposition that square root of 3 should be close to 2 because square root of 4 is 2. When we can substitute x0 here in the 1 over 2, 2 plus 3 over 2. Compute it, please. Compute it. And find x1 using x0 as 2. What is x1? Apply this formula. And when applying on this slide, for example, we compute square root 17.
7/4.
Wait a minute. Square root of 17. What can we take as initial guess? We can take 4. Why?
16.
Because 16, square root of 16 and square root of 17 is close to 4. Okay. When you use x0 equals 2,
7/4. No?
I don't know.
Yeah, 7/4.
7 by 4? It's 2 plus 3 over 2.
Yeah.
Two plus, yes. But it's better to use it's better to write it as 1 point what? Not 3 over 4, but 1 point 3 over 4 in decimal. 3 over 4. Use a notation with point. 1 point 5. 3 over 4. You can use calculator. 7.5. It's 1.75. 1.75. It's better to use this notation because it doesn't require to compute all of their numbers in mind or in paper. You can use calculator to compute it. Well, I ask you to take 1.75 and compute x2. How to compute it?
You just put
Put here 1.75 and compute x2. Of course, it's hard to compute in mind. Please use your calculators to compute. One over 2, 1.75 plus 3 over 1.75. You can take 1.75 in the right hand side of this equation.
it's 173.
1
73.
points. What 70? Write in your papers these formula and after that compute it using your calculator. Just write it, 1/2. Substitute here 1.75.
173.
But with some numbers.
Yeah.
What numbers? 1?
73214.
1.732142 4 and so on. It's enough. It's enough. This is x2. How to compute x3? Take x2, put it in the formula, and compute it again. Well, now compute the real value of square root of 3. Use your calculator and compute the real root using calculator. What is the real square root of 3? Or I can do the same. 3 square root. This is a real value of a root. The real value of square root of 3 equals to 1.73205. Well, you see that the initial guess is far. This point 1.75 closer. This point 1.732. 3 digits is the same. And 1405. The difference is in the 4th digit after decimal point. If we continue, we get the same result. And my point is that this value in the calculator is computed using this algorithm, because computer can implement only the algorithm. It cannot compute square root. It cannot compute sinus. It cannot compute cosine. It can just add 2 numbers, subtract 2 numbers, multiply and divide. And all of the functions are computed using these elementary functions. Subtraction, division, multiplication. Like this. This formula includes only addition, multiplication and division. And as you see that just a few steps of this process and we get more or less correct result. Please do the same. Please do the same for square root of 16. Square root of 17. Just to reproduce these results. Just reproduce the results that is written here. Suppose that we are going to calculate square root of 17. How to find square root of 17? We know that square root of 16 is 4. And we can take 4 as initial guess. x0, x0, 4. R is 16 now, because we are going to find square root of 16. Please find first two values, x1 and x2, for square root of 17. Oh, sorry, R is 17, of course. Square root of 17. R is a 17, square root of 17. you get 4.12 as the first point. Right? Can I? Yes, it's 4, and here is 17. 17 over 4. Mhm. Over 8 with 2 point. No, it seems wrong. The result is wrong. Check your computation. Okay, but please compute it as there. It should be 33 over 8, not 21. Why 21? 4 times 4 is 16, right?
It's
34.
1, 2, 5.
4, 1, 2. Yes, 1, 2, 5, right. The first digits are 1, 2. The first two digits, right. And after that, use this number for the second.
No. I ordered something to drop it in security. So I left it in
Mm. 33 over 8 and compute it in decimal fraction. Right, right. So the first answer, so it should be 5. 4.125. After that, please take x1, 4.125, and substitute it into this formula and find their x2. Find x2. Did you get the x2?
Some?
Yes.
Mm-hmm. The same digits after.
Yes.
Mm-hmm. Well, let's compare the result that you get using two steps of Newton method with the real value of square root of 17. The real value of square root is 1,2,3,1,0,5,6. So just two steps of the method and we get the result that is very, very close to the
I found
actual.
for 18.
Open one, two.
But well, it's better to use this value and not just substitute x1 in this form and use calculator to compute it. That's all. Right. But you see that the real value of root is 1,2,3,1,0,5, and in your case, in our case, 0,6. So the mistake is only in this digit. These digits are correct. These digits are correct. So just two iterations of the method, and we get very good result. Very good result. And okay, finally, let's solve one more exercise. Let's consider one more example. The exercise number 1. Let's consider another formula for cubic root. F of x equals to x power 3 minus 2. Let's consider the example. The exercise number 1. Square root of 3 minus 2. Or x power 3 minus 2. F of x equals to x power 3 minus 2. This function corresponds to the value of x that equals to square root of 2. Sorry, cubic root of 2. Cubic root of 2. Again, I don't know what is the value of cubic root of 2, but I know that root of 1 equals to 1. And I can take 1 as initial guess, initial value for this process. X0 equals to 1 minus 1. What minus 1? You should use this formula.
Derivative.
Well, first you need to find a derivative. 3x squared, right? The derivative is 3x squared. After that, you should substitute here the function and derivative x n plus 1 equals to xn plus x squared minus x cubed
X cube.
cube minus 2 over 3x squared n. Well, in general case, we cannot simplify. In this case, we can also try to simplify this formula, but in general case, we cannot simplify. You just substitute the value of x0 here and find x1. Try to do this step. Substitute x0 and find x1 using this formula. Minus 2? No. X1 minus 2?
No.
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 Take.
It's 2 over 3.
It's very simple. It's
It's
minus
2 over 3.
2 over 3.
Yeah.
No.
Minus 1 plus
No. It's 1 minus
1
Oh, 2, sorry.
2 over 3.
2, yes, right.
Yeah.
2 over 3. 2 over 3.
yes.
So yeah.
My 1. So 1 is a bad approximation. Wait a minute.
1 minus 2 minus 1. 3.
Right, 2 over 3.
Yeah.
How to find the next point?
The same one.
Take 2 over 3. Take 2 over 3. Substitute here, here, and here.
You need to find it.
And no, I think you understand.
Yeah.
It's just a computation. It's a computational process. Of course, now nobody can apply this formula using pen and paper. This process can be implemented on computers. This process can be implemented. And, well, now we have some time, and I want to discuss with you about theoretical properties of this method. Theoretical properties of this method. And the main theoretical property, the main question is what error we get after some steps. Because you see that all of the methods that we consider, these methods cannot solve the problem exactly. But these methods can give us some good solution that is close to the real one. And you see that applying this method, we can get solution closer and closer to the real solution. But in some cases, the method can diverge. The method failed to solve the problem. Please look to this picture. suppose that the function f of x looks like this. F of x. Very simple function. This function has only one root, this one. Keeping in mind this graphical interpretation, let's imagine how the method will work. Suppose that x0 is this point. This point is x0. This point is x0. Then we compute f of x0. Then we find the slope of the tangent line, and we find the intersection of the tangent line and zero axis, zero line. This is the point x1. We find the value, we find the tangent line, and find the intersection. And after that, you see that no intersection, because the tangent line at this point is parallel to the x. It never intersects. So the method failed to solve this problem, or we can say that the sequence will diverge. And the method will work when we suppose that the initial point, our initial guess x0, is sufficiently close to the real solution. This is the main drawback of this method. When we consider the bisection method converges to the real root from any starting interval. We can take very, very long interval, and after that take half, half, one half, another half, and we converge to the real solution. Newton method is a good method, it's a very fast method, but if we take initial guess far from the solution, the method can diverge. This is an algorithm described in the form of pseudocode that you can use to implement this algorithm on computers. What is the initial information? Of course, to apply this method, we should know the function and the derivative of this function. Also, this is the main feature of this method, that to apply it, we should know f of x and f prime x. If we know it, we can take x0, we should fix the tolerance and their maximum number of iterations. The output information is the solution, the approximate solution x, or message of failure. Let's set the counter to 1, and the main loop can be organized as follows. While I smaller than n, and the length, the distance between current point and next point is greater than tolerance, let's update the point. Let's compute the next point. We reassign this point. X is the next point, x0 is the current point. We update x0 and compute and update x. using this formula x0 minus f of x 0 over f prime of x0 and increase the counter. If the number of iterations becomes greater than n, the method stops. So the main loop, the main formula is very simple. Just apply, apply, and apply this formula. Well, I briefly show you this implementation in C++. And I ask you to implement this method as their homework. But I show you this implementation now.
Sergey Viktorovich. Не Викторович. Здравствуйте, какой мама?
Well, please look to this. To apply this method, we should write two functions, f of x and f prime x, derivative of f. For example, if we consider the function x minus 2 power minus x, the derivative of this function will be 1 plus 2 power minus x logarithm 2. And how to write the main? Exactly according to the pseudocode, we should introduce tolerance and number of iterations. It can be assigned from the keyboard, it can be input from the as assigned in program or input from the keyboard. Well, if the distance between next point and current point greater than tolerance and k is smaller than n, just 3 lines inside loop. Reassign x0 and reassign x1. That's all.
So what does FABS mean?
F ups, absolute value, float, absolute. In clear C, it was the difference between F ups and ups. Now in C++ you can use just apps to write absolute value, but I use F ups to indicate that this value is a float. Well, let's run the method. Number of steps, for example, 10. Tolerance 1e minus 6. And the solution is obtained after 4 iterations. Let's check, let's output the value as in previous case. Let's output, I can just copy this line. F of x1 at the point x1. N and 1 e minus 6. Well, we have the value that is very close to 0 at this point. Very close to 0 because just the compiler outputs it as 0. Let's use another tolerance, for example, number of steps 10 and tolerance 0.01. We have just 3 iterations and the value of the function is 10 power minus 11. Is very close to the real solution. So you see that this method is very powerful, it's very good. But we need to take the good initial point, the good initial guess, x0. Well, let's come back to the presentation. I close this screen. I come back to the presentation and we have just 10 minutes and I just briefly discuss about the error. Maybe I skip some formulas, but I want to discuss with you about the main point of the error analysis. In bisection method, you remember that we take 1/2 of the interval at each step, and the error becomes twice smaller at each iteration. Here, in Taylor's, in Newton method, we also can estimate the error as a difference between the point xn and the real root r. So the error at the step n can be considered as a difference between the point xn that we compute and the real root r. And maybe I skip all these computations. I also want to discuss with you about this final result. Again, En means the error on the step n. En plus 1 means the error on a step n plus 1. And this last formula tells us that error on the next step, E n plus 1, it approximately equals approximately equals to some constant C, constant times error on a step n in square. This is a very good result. And it's very simple to explain. Suppose that this constant equals to 1, for simplicity. This constant equals to 1. And suppose that En, the error on a step number n equals to 0.1. What can you say about En plus 1 according to this formula? Constant equals to 1 and En plus 1 equals to En in square. En equals to 0.1. Again, 0.1 in square. What is this value? 0.01. So En plus 1 equals to 0.01. What can you say about En plus 2? Three zero 0.0001. If you compute En plus 3, 7 zeros. 7 zeros and 1. 7 zeros and 1. The error becomes significantly smaller at every step. And this is called quadratic rate of convergence. The next error equals to current error in square. If I have at the current step error 10 power minus 1, next step 10 power minus 2, next step 10 power minus 4, next step 10 power minus 8, next 10 power minus 16. It's very fast rate of convergence. So it accounts that the precision is doubling with each iteration of Newton method. This formula can be derived exactly from the Taylor's theorem. Well, we consider two methods for solving nonlinear equations: bisection method and Newton method. Next week we will have one lesson. We start 10:50 and we consider the last lesson, the last method for solving non-linear equations, so-called fixed point iteration method. We discuss about fixed point iteration method because these three methods are used very often in different fields of mathematics. Do you have any questions? No questions. Well, I stop sharing the screen and I also stop recording.